So hello, my name is Boguslaw Cyganek, and I came from Poland. And let me present myself. So you see the subject, I will be talking about serial parallel pipelines in modern C++. I will explain why I took this subject later. But what I'm doing for my entire life is working in scientific research. So my main domain was and is computer vision, and also this revolution of artificial intelligence, machine learning. But I also program systems, and I teach C++. So for years I was writing C++ software for computer vision, embedded systems and desktop systems and so on. Actually, at some point I was doing parallel research to this, what we call now OpenCV, which is much bigger platform than this what we did. But anyway, as I mentioned, I'm teaching C++. So at some point I found myself looking for information on recent libraries like studranges, and I was looking how to explain to the students how is this pipe operator built, how it is implemented, and I was looking for some materials, and then I was starting writing some examples, and I came to my own solutions. So we will see how does it work. So this talk is not about studranges, but it is about more general programming paradigm called functional programming. And here you have the agenda. So we'll start with pipelines, pure functions, things like this. Then we go to build our own pipeline, and I will present you stud expected. I don't know if you have used that object, that class. Have you used that class, some of you? Yeah, I will show you a couple of cool things with this. I'm really a big fan of this class, of this object. And we'll show also a parallel version of this pipeline framework. So the most important is our own overloaded pipe operator, and this expected. It will be on the green pages, and on blue pages we will see parallel version. So I hope this renders well, because I have a lot of code to show. Okay, let's move on, because I have a lot of things, and I am quite non-linear as majority of physical systems. So I start slowly, and then I need to move on. Okay, so what is a pipe and what is a pipeline in software architecture? So maybe you can think of such mechanical pipes. That's good intuition, but we have something what resembles them. So when we read in the Wikipedia, we see that this is a chain of connected. I call them nodes. They call them filters, and the characteristic is that one is passing results to the other. And so we will start with this version. Certainly, you can have some. The pipes can be split at some point. They can be joined. We'll not go that deep. We'll show you only the basic pipeline, but you can. I will show you how it can be extended. So that's the definition from Wikipedia. So that this is a chain of processing elements. You will see that it can be mostly functions, but you can have threads. And interestingly, you can have also coroutines. I don't cover coroutines here, but I have this on this separate talk. Okay, and we can have different types of pipelines. So you can Google up what is a pipeline, but probably you know very well. So pipes in software engineering, let me start with some history. So I know these times a little bit. When Unix started, I was programming. My first machine was VAX machine, and then we had PCs. And so a pipeline, we know pipeline very well from Unix, from Linux. So pipeline is a way for inter-process communication, which message passing. So we can join a number of processes, output of one to the input of the next one with this pipe operator. Yeah. So we can write in the terminal. We can write such a command, and we have pipes and we have redirections. They are different, but they have some commons. We will not go into this, but an interesting story happened in 1986. Probably you know famous Professor Donald Knuth, and he was asked by John Bentley, who was at that time editor of programming pairs in communication of ACM, to show his skills of programming, because Donald Knuth was developing, for example, his famous tech for text assembly was his language. So he was asked to show a solution for a program for counting word frequencies in a text, and he did it. And his solution took many weeks to develop, and it was code very precise with new hashing trees, all this stuff. And he was showing this literate programming, which is also interesting by itself, because it is just putting comments and code. Now we have kind of this with ChatGPT, for example. We only put comments and the code is generated automatically. So this is what literate programming was about by Donald Knuth. And probably you know this famous set of books. So his implementation was very clever and very, very good, but quite elaborated. But at the same time, Doug McIlroy, who was an expert of pipes in Unix shell, he came out with this solution. So he wrote a couple of lines. Probably you know what they do. They translate non-alphabetic characters to new lines, then all upper cases to lower cases, then they sort, then we find unique values, and we sort again in reverse order, and we print them out. So this took only a couple of lines of a pipeline. So certainly this solution was slower, but the task was not to make overperforming. Sometimes we can sacrifice performance for short code, like in this case. So this is an interesting example, and we will return to it at the end of this talk. So we have finally in the C++ functional programming, we have pipe operator because we have stud ranges. This is warm-up, what we can do with stud ranges, but as I mentioned, this talk is not about ranges, but certainly we'll have them somewhere inside of implementation. So we can join our pipelines with the pipelines already provided in stud libraries. So therefore, I named this talk in modern C++. So for example, what we can do, we can traverse this vector of values, we can filter, and then we can transform. So you see the natural, the first thing we teach students, natural things of embedding functions in the functions. So this is supposed to work fine. And you have this output, you take only positive values and then multiply by 2. But the much more pleasant and verbose is just to use this pipe operator. So probably this is what makes stud ranges library so nice. This is the last. I hope this is well seen in this contrast. Well, maybe. Okay. So this is what we do. So actually calling a function like this complex composition of functions is equivalent to making a pipeline. A of R is equivalent to R pipe A. Okay. So this is, yeah, I already justified how I came to this talk. So just looking for some materials to show students how this pipe operator is implemented. So I started to implement my own. Then I found a couple of good materials which I would like to share with you. The book by Ivan Čukić is a very interesting one. I recommend this. And also I found this talk by Ankur Satul. And the beginning will be just after Ankur Satul, what he did with the pipe. So let's go smoothly with his solution. So he proposed something like this. So, and probably it can be sufficient for many tasks. Actually, you can supply almost any data in the form of a string, even image, digital image can be translated to characters. So we have a function which takes a string, returns a string, and that's the simplest solution. So that solution is just to make you an intuition of how does it work, because details you can look up in my code, or you can play this recording again, but just for you to, how does it work, what it is about. So this is very simple. We can write this code and it works. So here we see the simplest version of a pipeline with the same interface between the nodes. I call these filters, these functions, I call them nodes. Okay, so yeah, I already said that. And we use this right references here. And yeah, the callable must accept a string and return a string. So here is the simple example. It's too simple to spend time on it. Just to show you how it plays in practice. To show you that it is a couple of lines of code, you can make it in your code. If you see the pipeline, you can write such a code, and in simple cases it will work. Then you can set up your pipeline with your own pipes, and they don't interfere badly with stud ranges, and we'll come to this later. So they can live together. And here are the results. So what happens if, yeah, this is the solution we came up right now, but what if we have different interfaces? So not necessarily string. So we start from a string, then we change the string to a value, then we change that value to something else, and so we have such a pipeline. So we need to come with different, more elaborated version. So now we'll have any type. We allow any type, not only strings, and we take a function which will process this type as its input, and what is a return of our pipe operator is a result of calling that function with this type T. So that's the intuition. Certainly we need a couple of templates, and we have this requirement. We have this. So this is not ranges what we are using, not to interfere with the ranges. Okay, so here we have a concept that requires not stud ranges of T. But ranges can be inside our code, no problem, thanks to these requirements. So the compiler will know when to choose stud ranges operator pipe and when to choose our own. Yeah, and again, function parameter is just T. It can be any parameter. And we can add const expressions, certainly. If we know parameters and the compile time, this can be compiled, invoked, and the result can be put back. So we know these things about const exp. And we have this return type again underlined here. So we use also, probably you know this function. It will be a number of functions shown in my talk. If you don't know stud invoke, just look it up in CPP reference. It is better. I can write a function of a parameter of type T, but stud invoked is more general. It can be used with any so-called callable. It can be a member function, it can be a pointer to a function, it can be pointer to a member, and so on. So that's the thing we'll use. But we have a problem. Not the only one today. But what to do, and this problem was already raised by Ankur, what to do with errors. Yeah? We push something and something happens. How to deal with this? Throw is natural first answer. That's fine, but you shut up the music. You just throw and you go out of the... Maybe you can do something. Maybe you can do something on the way. So there are many possibilities. You can pass the errors. Okay, if I'm a node and I'm receiving an object with an error, or I'm producing an error because I cannot compute something, I can pass an error. So what other nodes are doing? The simplest solution is they are just skipping their own operation. They pass this error till the end. But it can be, and this is in my proposal, you can try to fix it. Or with fixing, you will encounter another error. So this is more flexible. But so Ankur proposed at that time to use stud optional. So this is the first thing. What is stud optional? It can contain an object or not an object. I mean, it doesn't have an object. Back years, we implemented this with a pointer, and a pointer having null value, no object. But now we have a stud optional, but we have something better. In a moment, I will show you. Well, this guy is stud expected. Because stud optional allows us only the first thing. We can pass only, okay, the error happened, we have no object, no other way, and we pass this error till the end of the chain. But we have stud expected, so if you take the only one thing from my presentation, just please play with stud expected. It is changing the way we implement interfaces. It is really a really powerful object. And now let's look what it can. It supersedes optional. So this is based on, so now we have green pages, and green pages are about stud expected. So I copied a couple of important information so you can learn about stud expected in 5 minutes. Not reading the entire CPP reference, which is great, but learning from CPP reference is discouraged at the first shot. Okay, so at least this is what I am saying to my students. So stud expected can have two objects or two states at a time. Either a valid object or an error, which is another object representing an error. And it distinguishes the two. That's the virtue of stud expected. Yeah, and you have, it is, the other good thing is that the value is stored, in this object, no allocations. There is stud unexpected to represent this error state, but it can be, well, we'll devise some interfaces with this later. Some types are discouraged as objects, but the most important thing for you when you deal with stud expected, always check if it contains an object or an error. So you cannot dereference an object if you are not sure there is a valid one, because this is not throwing, this is even worse thing, which is UB, undefined behavior, for some reasons. And we have monadic operations. I will not talk about monadic operations, but they can provide pipeline by themselves. So you don't need to write your own pipe operator. You can use monadic operations. This is in another of my talks. So and it can be used instead of optional. So we have a constructor, and this most important Boolean operator. We can dereferencing of an object. We can have a value. If we know that we have an error, we can read out an error, or we can have another value just in case, and we can compare and many other operations. But from this, please recall what I mentioned. Just always check if you have, like with pointers, you need to be sure that if you are accessing a value, it is the value. So simple example, as I mentioned, I am from science, so we do a lot of things with tensors, vectors, matrices. So many times we do some normalization of a vector. This is the formula. You need to divide a vector by its length. And let's create something with stud expected. So look at this. I created norm expected, which accepts a container. This is template type name provided, so we can provide different containers into our template. So it will work with arrays, with actually majority of containers for which we can dereference the elements. And so this is our expected, and we write normalized function which returns just this expected. Why we use this? Because this function can fail in a number of ways. You will see in a moment. So we accept the vector, and there is also another interesting thing. We use this concept of allowing only floating points here. This is very useful, recent feature. As I promised, we are using modern C++, so we put these concepts. And contracts, in some sense, you will see in a moment. So first, if we see that the vector is empty, we return stud unexpected with an error. But if it contains something, we compute this denominator as an inner product. Then we check if it is big enough. Please remember, don't only check if it is different from 0.0. If it is too small, you cannot divide the values because you will have wrong results. And also you can check if this is one of some weird floating point values like infinite or not a number. And you can look it up in one of my talks from back years on floating points if you are interested, but there are many good talks on floating points. And then we transform. If we know that we can divide, because the value is big enough, so we transform. So this is a very simple example. We'll be using this later on, how to change our implementations to using stud expected. And now we can run certain of things. Look at this. I generated a couple of vectors. And almost the last one, I tried to divide by 0 to have not a number or infinite value, but the compiler was too smart to compile, so I had to use this sinus of 0, which is 0, and I am actually dividing by 0. And when we run this function, look at this, we need to check if the result has a value. That's the most important thing. So this is the pattern of using stud expected. If it has, we can print it out. If there is an error, we can do something with this error. So, yeah. So the results for our vector, we see that only the first one and the last one can be normalized, and the other in the middle, they produced some types of errors. So let's return to the pipeline. Now we know how stud expected is working. Okay, we had this problem, so this is why we use stud expected, but we'll see stud expected in a play later on as well. So our pipeline will be like this. This is the pipeline I built. So we can use any function, and we impose on this design that we deal only with stud expected, but they can convey whatever object we wish, but also they can convey some errors. So there can be different inputs, different outputs, but they must be compatible when they exchange. Yeah? So that's understandable. Okay. So here is the implementation I provide. It's very similar to the last one, but we deal with stud expected. Look at this, how many stood expected we have here. So we have also this concept here, just to be sure that someone is not calling with not stood expected. So I implemented this concept because I couldn't find it. I have const exp as well with const parameters, so we have a number of versions of it. And we have this concept here. So we require that it has the value, the error type, so it is stood expected. But what is interesting, if I don't know if you are using concepts already in your code, someone is using or trying. Okay, that's also a cool part, but also requires, like this requires some, we need, for example, to write here, requires to force the compiler to check the value. If you omit the values require, the keywords requires here, it will only check if this is syntax correct. Okay, so now we have, that's it. We have a serial pipeline. So let's make something useful. We deal with vectors. We know this is the era of AI. We do a lot of ChatGPT, other things, so we need to encode words into some encodings. This will be vectors, so let's do something very simple. And we need to encode some images even to embed embeddings. This is called embeddings, some internal representations from transformers. And we need to check out compatible or similar images by looking up at their corresponding embeddings. So how we do this? And how to compare vectors? We can use such a thing like cosine, which is used actually in ChatGPT and other transformers. And this is very useful if we have already normalized vectors. So this is why I showed you this example with stood expected at the beginning. And yeah. So what does it mean? If these are different vectors in different directions, so this is like fire and water. So they are totally different. So the result will be -1. If they are concurrent, let's say. Sorry for who likes Pepsi or Coke, I don't know. Okay, let's say for me this is the same, so the result will be close to 1. And if they are the concepts, okay, is something to drink, so they are somewhere similar, so the value will be 0. So this is a good measure actually. So actually in science, majority of work is to find the ways of comparing things. So finding good, we call this metrics. So we have the simpler one. So okay, what we do, we have a number of files. Each file contains vectors, so we need to load them. They are not normalized. We need to normalize them. Then we need to compute such a matrix to compare each with each. So it is triangle matrix, and find the best match. So it will be, for example, our image to all the images in the database. Okay, or on my phone. So this is a pipeline. So this is the first example I came with. And we'll see a couple of things on the way. So let's implement this very fast using stood expected. So always when dealing with stood expected, we need to have an object to process, but also we need to write out all the potential errors or unknown situations. So we usually have this enum class with some errors, and we have some like here we have a file path, but the file can be empty and so on. So we go like this. So we wish to load all the vectors, and again, very characteristic thing, at the beginning of a pipeline, we always check if we encountered an error at the beginning. If we did, we either pass it or we do something with it. So that's the flexibility of this. If you are using monadic functions of stood expected, have anyone used monadic? Yeah, there are different rules a little bit in this pipeline with monadic. Okay, and then we use directory iterator. Is classical stuff. We push all the paths for further processing. And if we use pure functions, the functions which don't change the external state of the word, that is even better. So another function in the pipeline, load vectors. Again, let's check if we have an error on the beginning. If not, we go and we open each file, we read each line of code, and we place back to the vector. And at the end, in the end, we can return either the vector if it contains something or pass an error. But this is the problem I encountered. Okay, so I have one type of errors, let's say set of errors, another set of errors, another set of errors, and I would like them to cooperate in a pipeline. So if one node encounters an error, it can pass the same error, or it can create its own error and pass by. So how to deal with so many different errors? And in C++, we cannot inherit from enum class, from enum. I tried to embed them in classes and do some cranky things. It is not working, but the solution I came is use stud variant. This is another cool object we have. Have you used stud variant? Yes, great. So variant is the thing that can hold a number of objects, but only one at a time, of special type. So what I did is common errors. So I redesigned these interfaces you saw to use these common errors. Okay? And now each node can deal with each type of error and can do something. Okay, so here are our interfaces, final interfaces. So you see expected with different objects, because each node is processing different objects, but with the same set of errors, but not all errors at the same time. So the node can choose which type will be passed by, but it can process all of them. The drawback of this solution is if you extend your software, you need to change the software to extend your variant. Yeah? Or maybe you can do some clever things with templates. And we have change interface. I don't go with the code. Okay. And finally, we have normalize. You already saw this thing. So we compute distances. So again, we can have an error at the beginning. So we check it. We construct a square matrix. We compute the distances. This time we call inner product. We have such a function. We have also map reduce if you wish to use parallel versions. So we have a lot of good things. So that's it. And we almost are done with this pipeline. And finally, we are looking for the best match, which is close to 1. So finally, we have the entire pipeline. So sorry, we skipped to the code, but it is quite simple code. But this is interesting. Look at this. So what I need to do, I create the initial path to the directory or a folder with all my files with vectors. Then I need to call the function load paths. But it accepts 2 parameters. But in a pipeline, I can have a function which accepts only 1 parameter. Yes? So what I'm doing here, lambdas are coming with help. And this is called function querying. Just getting rid, the process of getting rid of one of the parameters at the time. It is named by the name of Haskell Brooks Curry, American mathematician. But other nodes go like this. Look at this. Yeah. And finally, we can process the result ourselves in the lambda. So I think it's quite clean and verbose solution. Look at this. You can quite easily add something to this pipeline. You can take off something from the pipeline. You can test functions in the pipeline quite easily. That pattern has a number of... So what we do, if we have correct answer, we check it because it is expected, please remember, and we print it out. And interesting thing, if we wish to process an error, we don't know which one will be, we use such an overloaded, and the only reason of this overloaded pattern is to bring up this function operator. So, but each of these lambdas or other functions must be different, must take different parameters. So the compiler will choose the right one to print out, in this case, the correct error code. So this is another interesting thing. And here is the example. I will skip it quite fast. The interesting thing is, okay, results, good results are not that interesting like bad results. So what happens if I forgot to put some numbers inside the file? I have an error, and indeed the answer is wrong data from this pipeline. But we can do better, and this is the question I put myself a couple of months ago, if I can do something to make this pipeline operating in parallel, like processors do. Okay, because we know we have pipelines in processors, they process instructions in pipelines. So how does it work? So this is a serial pipeline on the left, yeah? And this is the parallel version. So in the first step, no difference. We take the green, at least I see green, we take the green element from out of the queue. Then, in the next step, this green is processed by first element, F0. But look at this. On the parallel version, already another element is ready for processing. Okay? And in another step, the serial pipeline is still waiting for this green to be processed entirely. And well, imagine we have 12 or 20 elements in a pipeline. So we wait 20 steps to process one element. Well, this is well known from basics of computer science. But if we can put it into our framework. So let's start with a serial representation, which is like this. This is the same slide you already saw. I redraw it a little bit. It is the same, but now it's different. So what we did, we put a thread or threads for each node. So each node can be processed in parallel, in consecutive. And we need to endow with this solution with queues, because we need with synchronized queues, because on the interfaces there are some producers and consumers. Okay, so that's the complication we have. So what we have here, we need to redesign overloaded pipe operator. We need to do the threads, and we need thread functions, and we need to implement the queues. So let's take a look in each of these three problems now. Okay, so here is our pipe operator. Look at this. It's not very different, but the input is the queue, is the shared pointer to the, well, expect. I will be using stud expected to implement the queue. And actually, it will help me to avoid blocking of threads. We will see in a moment. But I call it cartridge function, can be as previously. So what is the difference now? Well, the thread is orchestrating, so the function is picking up from the queue and processing and putting the values, okay, to the output. So, yes, the output. So now the interfaces, in serial representation, it was stud expected. But now we have another indirection. We have synchro queue of stud expected and synchro queue of stud expected. So that's, well, we need a couple of type names, requires, expected, so on. But the most important is, well, my contract is assert. I'm using assert still. waiting for contracts to come to C++. And I create output queue, and the most important thing, we create the J thread, the thread, and we provide this thread with a function, which we'll take a look in a moment. So it's simple in the concept. We check if we have correct conditions, input conditions, then we create the output queue, and then we launch and we detach. That's important thing. So it will run by itself. So whatever you put, it will be processed, but we need to communicate with this thread somehow. So that's the tricky part. Okay, let's take a look in PowerPipe fun, that one. And by the way, I thought at the beginning I need to make a mutable lambda, but actually when I looked down into shared pointer, the reference counting part of shared pointer is separate from it. So if you know that if you implement lambdas, they are by default const. So, but in this case, it doesn't matter, fortunately. And you can launch many threads in this operator, which I did, but I refrained myself. So now we have the threads, how the threads operate. But I made a very important decision. I allow only one thread per node. It is a constraint, but also it solves a lot of things, especially communication of threads. So, yeah, we'll come to this. So this is a function for a single thread. The input queue, output queue, cartridge function, so what it does? It rotates and it reads from the queue, we'll come to the queues in a moment, it reads an expected element and it checks if it is a valid element. And if so, it invokes the cartridge function and it pushes the result of this function out onto output queue. If it is not, it must be our sentinel. So what I did, I put an expected to another expected. So we have embedded expected. So it's a kind of a chain of expected. Why? Because this way I can model the sentinel like an error in the synchro queue. That's the point. So here we have a sentinel. If we encounter the sentinel, we stop the music and the thread goes out. Okay? That's the means of communication with the thread. So it simplifies a lot of things. Okay. And the queue, yeah, we need two add-ons. The first is to synchronize the entire pipeline, if we wish. So we have an overloaded operator, pipe operator. Look at this. We wait for the sentinel, and we return the queue. And the sentinel is just a placeholder, just a type. And the second is just to process the entire queue. So I'm not processing element by element in the queue. I take the queue and I can produce anything. So it can be used at the end of a pipeline. This is very useful function, okay? But also very simple. So finally, the same example but made in parallel. Look at this. I create the queue. Now my talk is about the queues, not expected. This is the queue of expected. And I have load vectors, vector normalize, then I synchronize because I need to collect all vectors to compute distances in this implementation and find max. And then I can process the result. The good thing is that majority of these nodes are the same software, like in the software, in serial implementation. So you don't need to have two versions, usually. And now the queues, we have not much time for the queues, but a few minutes. So why it is expected synchro queue? Because this is synchronized queue, but to avoid blocking whenever possible, I use std expected again. And std expected can me provide the information if I have available object for my thread, or I return no object, and the thread is not blocked. but the thread can block itself or can ask to be blocked just in case. So we have these elements. Look at this. My original element is called LM here, it's a type name. But elements I'm processing in this queue are expected elements. So these are LMs, and look at this. The errors we can have here are actually not errors, I can say, just states. Element is not available, or the element is a sentinel. A sentinel means stop the music, just stop the queue. And we have push LM. Yeah, okay. We have push LM, push sentinel, pop, don't block, pop wait can block. We'll come to software, to implementation in a moment. Check for sentinel don't block, or wait for sentinel can block. So we have options here. And the internal objects I used is queue, mutex, and conditional variable. But I was also playing with some atomic representations, but surprise, they are not always faster because of interaction with operating system, with other things. Blocking can sometimes be better. Okay, so how is push element implemented? We have this element, and we do a unique lock with mutex, and we push on the queue, then we notify. This classical stuff from the books, I would say. Okay, and push the sentinel, look at this, again, we log the queue, and we check if there is an element, then access and dereference the element. So we check if the queue is empty, or there is something on the queue, then we push the element. Else, we try to be sure that we already have a sentinel on the queue. And we notify again. Pop, don't block, again. And this is interesting part, if empty, return expected with the error set that this is empty, don't block. And if there is something, you can pop it out and return the element. And now the version with blocking, okay, you have conditional variable and you wait for the queue not to be empty. And if not, and so on. So this is classical thing, but we have these two modes of operation, just to avoid blocking if we can. And example, well, that was too short to measure the differences. Actually, the parallel operations were sometimes longer in execution. You need to remember this, that not always parallel representation is. So I wanted to build longer chain of processes. So I built it. And this is Doug McIlroy representation of my representation of word counting problem. So I measured on this because it is longer. It is longer because we synchronize at the end and than with vectors. So yeah, what I took is some text, number of times, and what we have, not very big difference, but we can have something which is maybe worth considering. So if my finding is, certainly it's natural, that if we have long pipeline and the nodes are computationally heavily burdened, then we can have some gain of significant gain. It's not a couple of times. But if we do another experiment, we collect all these files and we put async works, well, with serial this time. So what I'm doing here, I'm taking, okay, I had 11%, 20, so I moved back to serial pipeline, and I parallelize the entire pipeline here. So we have enormous gain, as you will see. Okay, but there is a price. There is a price. So look at this. We have parallel, but serial pipeline, it is really 4 times. Why? You can ask why. Is this insane? Yeah? But, yeah. Here we have so-called functional parallelism, and in the second case, we have data parallelization. So we have two different domains, and we can join them, but it depends on our measurements. So finally, the conclusions. Pipeline is good, or can be good, or can be useful. And also, I encourage you to use stud ranges. I know that there are some opinions about ranges, but when I started to use it, I like it. The only one thing I don't like it is that there is no parallel implementation yet in algorithms of stud ranges, but probably this will be sooner or later. But we can define very easily this our own operator and have our own pipeline. And stud expected, this is what I am recommending you very much. Monadic operations, if you are interested, you can make a pipeline just using only stud expected. You don't want any operators by your own, but they are tricky. So you can refer to my talk from last year, and there I'm talking about monadic operations. And, well, this is interesting technique with this variant to deal with different errors in the chain. Maybe you'll find such a problem in your code. And the pipeline, yes, the pipeline is also good for testing. So you can take one part of it and do some unit testing, and also the testing of the entire pipe. And there can be a parallel version as well. So probably the best recommendation is to use it when you have many nodes. I mean, in my implementation, one thread. So for example, if there is 12 nodes, there will be 12 threads operating. So this is enough for one CPU. And then the entire parallel version can be again made parallel, like async works and so on. So you can play with this. The good thing is that the building blocks, if you design them properly with stud expected, they don't change from serial to parallel. But in many cases, this is what I mentioned. And just play with different versions of parallelism. Function parallelism is different from data parallelization. So, in addition, each node can spawn its own threads. So that's a natural thing. The problems arise when you have interconnections between the nodes, or they can produce deadlock or something. But please recall, I mentioned pure functions. If you stick to pure functions which don't change the state outside the functions, so this is more safe. And in practice, always measure performance, because sometimes parallel solution, very elaborated solution, can be slower and more complex, certainly, than serial one. Okay, so I think that's it. This is my book for beginners. And there is also my GitHub, so you can find this code with some previous version on the GitHub, and you have some contact to me. So thank you very much. Are there any questions?
Thank you. Thank you very much for the talk. More of a comment, I just wanted to mention, since you talked about parallel range algorithms, there was actually a paper, I think it's 3179. I believe it might have already been accepted. So it's probably going to be in either 26 or 29. So they're definitely coming.
This is what I'm waiting for.
Yeah. Thank you.
Thank you. Okay, there is one at the back and another here. Okay.
So in the pipeline operators, each consumer, that's when the operator has to handle the errors from the upstream, and they all kind of like, accumulate towards the end. Is there a way to implement in this setup some type of short circuiting so that as soon as an error happens, you don't necessarily return an expected, but you return just the value, and the error handling is done?
Yes, that's the important point. Yes, in this implementation, I wanted to be flexible, so you can do whatever you wish. You can pass the error you received in the input. You can try to fix it, and then you can pass the correct object of your own, or you can pass. You see, okay, I cannot fix it because the file is missing or something. I pass my own error, or I can pass some other errors which are contained in this variant. So therefore, I created this variant.
Okay, so you don't have to throw the exit out of it, I guess. You'd be using just a separate kind of sentinel thing for early exit in the pipeline?
If I correct you correctly, if I understand this correctly, well, I think this is flexible enough. It depends. Maybe if you give me some examples, we can consider this later. What if? Yeah, but for majority of cases, I can live with that very well. The problem I had was before I found this stud variant working fine with errors, because then the node number 4 cannot generate the error from pertaining to the node number 1. But with variant, it can. So you can decide. Certainly, this is the matter of design if the node 4 should know about errors of node 1. But even if you stick to your own errors, you are flexible enough to pass them by. Whatever comes, you push it by, if it is an error. In many implementations, like this monadic, only one path is available. So either you process a valid object and you return a valid object on error, or you process an error and you pass an error. So there are some constraint. Here, you can do whatever you wish in, but there is a price. You need to check at the beginning if your object contains any error. In monadic operations, you are sure in your node that you already received the strip of object of stud expected. Someone else in the framework checked that for you. So look it up in monadic implementation, if you wish. Okay? There was a question over there, I think. Couple of them. No? You're just...
I have the same question.
Okay.
Hi, my question, this is very interesting, lots of things for me to think about, some of the current projects I'm working on, so thanks for that. My question is, if you know of any impediment to trying to implement such a thing with standard views instead of ranges?
Well, views are part of ranges library, actually. Yeah. So ranges is something what has begin and end implemented. Yes. So this is the basic definitions. But this doesn't interfere with definition of stud ranges. They are in different namespaces, and I was using stud ranges inside this node. No problem. Actually, I was not showing all the code, but you can find it out. And well, the examples I made, there were no problems compiling, because compiler, also because of these concepts I put in the, so not ranges are in the input, but even this fact that we constrained our interfaces to stud expected, this is something different what ranges expects. Ranges is not working on stud expected. So we are, even in this fashion, we are different. Yeah? So we avoid some clashes and some problems when compiling.
Thanks.
Hi, this is maybe a question, maybe a comment, I'm not really sure. But it occurs to me when we have like these deeply pipelined sort of architectures where you're going to have many threads active at once, you could have situations where your parallel performance is much worse because of things like cache thrashing, right? Like if you're, in your case, your data is moving through the pipeline, you probably want to reschedule to the same thread to keep your cache hot. But like in more IO bound process, you'd want to, schedule these pipelines to different cores.
Yeah.
You can't really get that with STD thread, but did you do any experimentation with that sort of like multi-core architecture? I think you mentioned you're doing one thread per node.
Yeah, good question. Yeah, well, not that deep. And my suggestion would be first think of clarity of code, of what you wish to do, because not always you need to squeeze out the topmost performance of your solution. But certainly you need to be aware of what is going on. So pipeline is just flexible in design. Yeah? If you need something on the edge, then make a pipeline and check if it fits you. If don't, try another one. You can have such a composition of block of functions and play with them. Sometimes, because, well, I come from the electronics environment, we do embedded stuff, so sometimes it is better to allocate one big memory, static memory, don't do any more allocations and stick to this and do your memory management, and that's the solution. But the answer, short answer is profile and see where are your hotspots. Yeah? This is not architecture to squeeze the last bit of your computer, okay? This is rather to build some verbose software, something would have clean blocks, which can be, I would say, the virtue of this solution is code reusability rather than, well, it is not a compromise of performance, but, well, certainly you need to pass different values from a node to node or from the queue to queue, but this move semantics helps in this case. So we have many pluses and minuses, but this is different point of view why we propose or why we are doing pipelines. Yeah. This is like this Doug McIlroy solution. It was well, way slower than Donald Knuth, but it is in 6 lines. So you put on the scale. I have 30 pages of a code, or I have 6 lines, which I can rearrange in seconds. Well, depends what I need. Okay. Any other questions? I think that's all we have time for. Okay, well, thank you very much.